Okay, welcome everyone to my continuation of what is algebraic graph theory. Today I would like to continue talking about the second largest eigenvalue, which is, as I said in many times now, not canonical, but still has some quite few cool applications. So next time I will show you a completely ridiculous and surprising application. And today's application is also pretty good. So it's related to a very important notion, recently became very important notion in graph theory, the X expansion constant. I will explain what that is. And as usual, kind of as usual in this game, this constant is really a number. It's really hard to compute, but bounding it is pretty easy. And we get beautiful formulas bounding this constant. And yeah, so the formulas are given by the second largest eigenvalue. We'll see as soon as we get there. But let me try to explain that constant first. So what we want to do is kind of what you should think of the whole time is that we want to kind of measure whether a graph has a bottleneck. So why do we want to do that? Well, think of some traffic, for example, traffic graph. So bottlenecks are always kind of bad. They slow down traffic. So you want to avoid them. And well, maybe you want to make something precise. In this case, we want to make precise what it means for a graph to have potential bottlenecks. Before we get there, we just define kind of the underlying notions. And it's pretty simple idea. So we have a fixed set of vertices S. So here's my graph G. G is the whole beast. Yeah. And here is the complement is G without S. Okay. And I would like to just measure bottlenecks. So I should somehow cut my graph into two pieces. Okay. So I cut my graph into two pieces. So S and G of S, and I count the number of edges I need to do that. So here, everything in red. So 1, 2, 3, 4, 5, 6, 7, 8. So I need 8 edges to do that. So given a subset, I count the number of edges I need to cut the subset from the graph, and I call that the number, the boundary. So the boundary is the collection of edges, and the size of the boundary is exactly the number of cuts I need. And I denote that number using the usual notation, delta S. Okay, so the boundary of a subset in a graph is just how many edges you need to cut away until it's disconnected. Not cutting into two. Measuring bottlenecks, cutting into two. Not quite there. What we need to do is the following now. So what I want to do is really, as I said, I want to cut my cake. Graph, of course. This is a cake, I guess. But anyway, I want to cut my cake into S and G without S. And I want to kind of count the number of kind of cuts that I need. Turns out that this is, and then I would like to minimize those, but turns out that this is not quite what I need to do. So I minimize the number of cuts that I need to do to disconnect S. So I minimize overall S. But that's a bit boring because you could just take one vertex, right, as a set, and then this would be just the degree of that vertex. So if I wouldn't do something to this notion, I would just get kind of the minimal degree. But in order to make kind of fair cuts nicer, so a fair cut is like this one here. I have cut the cake, hopefully in some sense fair in pieces A and B, or S and G without S, which are roughly of the same size. To make those fair cuts more attractive, I divide by the order of my subset. So it's kind of better in this game to cut off larger subsets. And that's what we want, kind of to minimize over all possible cuts of subsets and normalized by the size of the subset. And this constant, which is associated to a graph, is called, well, either edge expansion or Cheeger's constant. And the usual task in this game, remember, we'll see that in the example in a second. So this one is supposed to measure bottlenecks. It will be very clear in the next example. But we definitely want to compute that number because eventually we want to check whether our traffic network, right, where the cars come in here, whether our traffic networks have bottlenecks or not. Okay, so we want to compute that number. But if you look at the definition, so you minimize over every possible way, it doesn't look like it's very easy to compute. You kind of need to, it looks like you need to brute force, just do all possibilities. And this is an NP-hard problem, so you probably really need to brute force go through all possibilities. So it's hard to compute. It's really difficult to compute. Before I give you a kind of a solution in quotation marks, how to compute it, let's have an example. Okay, so I have a sequence of graphs, and I construct them as follows. I put a kn here, in this case k3, and I put a kn here as well. So in my example here, n is always 3. Okay, so and I can now connect them using 0 edges, 1 edge, 2 edge, all the way up to n edges. So here's G3 because I have 3 edges connecting them. If I would have G0, well, then it's just disconnected. I just draw it here. So this is G0. If I would have G1, then I would have just 1 edge between them. Let's say something like this. If I would have G2, then I would have 2 edges between them. So something like this. And G3, 3 edges between them. And it's not so hard to see that actually the number, the giga constant, is minimized if you just take S to be, let's say, the left component. And then it's, well, how many cuts do you need? You need 0 cuts, so the constant is 0. You need 1 cut, so the constant is 1 over n, because the size of my S, it's kn, right? So it's n. You need 2 over n, so 1 over n, 2 over n, 0 over n, all the way up to n over n. So the number gets successively bigger, and the bottleneck successively gets smaller, right? So here, clearly, this is the bottleneck. Here, a less obvious bottleneck, and here kind of the bottlenecks are already gone. So in some sense, the larger h, so the further it is away from 0, the fewer bottlenecks, the harder it is to disconnect. So h is this measuring for bottlenecks. Okay, and we want to compute this constant, and that's really difficult in general. But here's an absolutely beautiful formula using the second largest eigenvalue, which is really, really, really simple. Just bounce this number between 2 very, very simple formulas involving the second largest eigenvalue. I'm a bit cheating here because I restrict to k regular graphs to get a slightly nicer formula, but there's a formula for general graphs using the second largest eigenvalue. So this is pretty beautiful, right? So hard to compute number, we kind of want to compute it again because of this bottleneck type, very, very applicable idea of measuring bottlenecks. And we can do it, or we can at least bound it by using the second largest eigenvalue, which is absolutely cool. And this notion came up quite recently. It's still already quite old, but recently in the sense of mathematics, by kind of the notion of an expander graph. So what is an expander graph? Well, an expander graph should be something that you would use for traffic. The traffic graph should be an expander graph. Computer networks should be expander graphs. The brain should be an expander graph. And what is an expander graph? Well, you certainly don't want bottlenecks, so the giga constant should be reasonably large, right? So a traffic graph shouldn't have too many bottlenecks. A brain shouldn't have too many bottlenecks. A computer network shouldn't have too many bottlenecks. But on the other hand, you want to be efficient. So the graphs shouldn't have too many edges. Kind of obviously, if you just throw in edges like many of them, you will have a large giga constant, but that's kind of very inefficient, right? You don't want to build 1 million streets. You want to build efficient streets efficiently. You don't want to have a brain which is a lot of kind of different connections, but you want to kind of do it efficiently. And the interplay between those two is what makes expander graphs so interesting. So they're kind of simultaneously sparse and highly connected. It's a very, very strange object, simultaneously sparse and highly connected. And usually you check whether they are expander graphs by using this trick here. And let me give you an example, because it's really not trivial whether they exist. Sparse and highly connected, kind of differences, kind of different notions. And so it's really not trivial whether they exist. And there are not so many examples, and it's always very exciting if you find families of examples. So here's a nice family of examples. So I have a prime number, and I can vary my prime. I can let prime go to infinity. In my example here, the prime is 59. So I have vertices from 0, here 0, up to 58. So kind of the remainders by division by p. So that's what my vertices, and I connect them in a circle. Okay, that's not very exciting. A circle obviously has a very small giga constant, because you can just take a subset which is very large, and then there will be just two edges. So that's not a good idea. But what you do is you kind of connect also to the inverses. And connecting to inverses mod p is kind of a rather random process. So the edges go around rather randomly. So let's have a look here. So here's the vertex 2, here's the vertex 30, and they are connected because 2 times 30, if I'm not mistaken, is 60. That could be true. And this is 59, which is my prime, plus 1. So mod 59, if this is 0, they're inverses, and you just connect along the graph. And because these inverting mod p is a rather random process, whatever that means, the edges are kind of arranged pretty randomly, which makes the graph extremely hard to disconnect. So homework is kind of check that using the second largest eigenvalue. Okay, so what I tried to tell you today is, again, kind of the same type of flavor of story you have in algebraic graph theory all the time. Like, instead of getting equalities, you can use the spectrum to get kind of really good bounds. And in this case, there was a really, really fabulous formula for the bounds with a really simple lower bound and a really simple upper bound using the second largest eigenvalue. Anyway, I hope you enjoyed this video, and I also hope to see you next time.